Thank you very much. And thank you for the opportunity to speak and to learn a lot about other nutritional elements from the other speakers. So it's been a pleasure to be here. In terms of disclosure, I was a member of the World Health Organization committee that produced their recent review on microparticles, plastics, but I have no financial connection beyond that, and that wasn't financial. We're all familiar with plastics. We know they have many positive attributes. They're frequently water resistant. They're excellent packaging materials in many respects, actually structural materials in many situations. Perhaps their primary negative element is that they are so stable in the environment. They do not readily decompose, biodegrade, or compost. And one of the fundamental reasons for that is basic chemistry and basic physics, and that is that they're not in solution. And so there really isn't, there's very little thermodynamic and kinetic driver for plastics to react with the environment that they're in. They tend to be particles. They tend to be, the ones we're talking about are particles. They tend to be very small. They tend to have high surface to volume ratios. But again, very slow to degrade because the surface chemistry just doesn't allow intimate interaction between the water or whatever reagent is in the water, be it acid or base or bacterium, and therefore they are very stable and resistant to decomposition. So it's the good news and the bad news. They are being found in ambient environment. They are being found in foods and in water. And we all are familiar with the situation of large quantities of large, bulky plastics floating in the oceans, acres of those things, which is, of course, just an awful situation. We're not talking about that today. We're talking about the microparticles, some of which may have occurred from that source in the ocean. But the microparticles that we're going to be talking mostly about are the ones that contact foods and drinking water directly. Now, in terms of those that are in the ocean, the microparticles, well, they can have an effect on aquatic life in terms of being, I don't know what the problem is, in terms of being ingested and therefore perhaps being concentrated to some degree in the organism. Now, as you would guess, in that application, it's most likely that the biota that accumulate those particles are going to be filter feeders, like clams, mollusks, and others. And so, but fish will also accumulate some microplastics, but the exposure from ingesting fish is a function of how much of those particles got systemic and then relocated out of their GI tracts into the organism. Now, it turns out that that's not a very efficient process. And so, in general, for fish flesh that is consumed, there really aren't very many indications of large amounts of plastics in the flesh. However, there are some fish that are consumed in their entirety, like small fish, like sardines, maybe. And so it's possible that there could be a greater exposure to that kind of fish rather than from a large, more of a game fish. But again, the primary exposure from sea life is going to be to filter feeders, clams, oysters, etc. Okay. So we're going to talk about primarily the chemistry, toxicology, and analytical science occurrence information that is associated with microplastics. And so as a subtitle, we might say plastic micro and nanoparticles in diet and drinking water. They come from a number of sources. Some of them are intended to be consumed or used as microparticles. For example, many cosmetics, at least to today, contain microplastic particles. They have an abrasive value, and so people are dealing with depilatory skin abrading agents could well be using a cosmetic product that has a microplastic particle content. And of course, so when that is washed off, it then goes into the sewer system, then goes into the environment. Those uses are being eliminated. Many countries have been banning that use, so those direct applications are going to be disappearing, if not already. However, a very large source can be plastic waste degradation, such as those large bottles, et cetera, that are floating in the ocean, or maybe even in some freshwater lakes, although not to the same degree. Very slow degradation products getting into the water, ultimately transporting downstream, maybe to a drinking water supply, maybe to an irrigation source, maybe getting into the surface soils, perhaps being taken up by some plants. So there's a chain that can transport even parts of those large, bulky pieces, once they're degraded, into the diet or drinking water and other water. And then once particles get into the wastewater stream, let's say used in the home or in industry and going into a sewer, well, then they go, in most countries, they'll go to a municipal treatment plant. And municipal plants are fairly good at removing those particles. They're not great, but they're fairly good. So a number of these particles are going to be concentrated in the sludge and the sediment that is then disposed of. How is it disposed of? Well, it might actually be put on land. It might even be used as a soil amendment. And so it possibly is being recycled into the environment once it goes into the sewer and then through the sewage treatment plant. And certainly when what is discharged from the sewage treatment plant, if it is upstream from a drinking water intake, then those particles will be found in the water intake, and then it's up to the drinking water plant to remove them. And they do fairly well. Now, the problem with the issue these days, though, and let's say it's been 5 or 10 years since this has been an issue as reports of detections occurred. The problem is that there are many reports, but as you'll see, most of them are of very questionable validity in terms of quantitation and identification. It is an extremely difficult analytical task to try to separate these microparticles or nanoparticles from the mass, be it a food mass or even water. It's very difficult to separate them, then to identify them, then to quantify them. And we'll talk a little bit about that, but the bottom line is, as of today, most of the data that you will see in the published literature by ostensibly qualified analytical chemists has deficiency problems with it. So take it all with a grain of salt. As we said, there are both microplastics and nanoplastic particles. The micros are the larger ones. They're usually in the micrometer, micron size range, where the nanos are a couple of orders of magnitude smaller than that, usually. We talked about food contact, but there are situations where food packaging can transport some microparticles into the food. And for example, apart from dietary food, even water, bottled water, of course, is frequently packaged in a plastic container. And there is a lot of data on detections of plastic particles of various types in bottled waters. So the concentrations that have been reported vary all over the map. We'll see some numbers, but they're typically probably realistic in a relatively small range. A few particles per liter, more or less. Sometimes bigger numbers, but more or less. And several organizations have reviewed this issue fairly recently. Food and Agricultural Organization did a couple of years ago, FAO did. They focused on sea organisms. EFSA, a couple of years ago, did a review, and just a few months ago, the World Health Organization did a review on microplastics and nanoplastics in drinking water. So I'll be talking mostly about those kinds of summaries. The bottom line is they were all quite consistent in their conclusions, and that is that there really hasn't been any significant, or actually any, human health outcome associated with dietary water exposures to microparticles like this. However, obviously, we don't know everything. Very little data is available on the nanoparticles. The nanoparticles are the ones that are small enough that are likely to be more transportable than the microparticles. So there's more to come. But as of today, there really isn't, there aren't any smoking guns, let's say, in terms of human outcome. Okay, what are they? There are a lot of plastics, many different kinds. The ones that have been most frequently detected in the diet or in water are polyethylene, polypropylene, and polystyrene. But there are lots of other possibilities, of course. There are plenty of polyesters that are out there. There are polycarbonates, there are epoxides. We know a lot of cans, for example, are coated with epoxy resins to stabilize and prevent corrosive effect from the metal can into the product. And even nylon is a plastic, of course. And among these many plastics, there are a lot of natural plastics too, by definition. I mean, we're talking about polymers now, long chains frequently of units. And there are plenty of natural polymers out there too. Starch is one, for example. It's biodegradable, but nevertheless, it's still there in particle form many times. So by size definition, microplastics would be those that range from about 1/10 of a micron to 5,000 microns, which is a pretty large range, and 5 millimeter size is really a big particle. I mean, that's a fiber. Nanoplastics are orders of magnitude smaller, ranging from about 1 nanometer to 100 nanometers. What do we know about them? What are their characteristics? Well, there are all kinds of different shapes and forms. There are fragments, undefined beads, pellets, spheroids, granules, all kinds of things. In almost all cases, virtually all cases, they have a high surface to volume ratio. So that's important later on because we'll be talking about contaminants in the microplastics. And so if they are very small, and if they have a high surface to volume ratio, that means that there will be an opportunity for migration, both inward and outward, from the environment into the particle and from the particle out to the environment. There are lots of additives that are used in the production and stabilization of plastics, plasticizers to keep them flexible, phthalates, DEHP, for example. A lot of other additives, antioxidants like alkyl phenols. There are dyes and colorants. There are titanium dioxide, sulfur, zinc, lots of things that can be used for particular purposes to promote the beneficial use of the plastic and its stability so it doesn't degrade in sunlight or in oxygen, for example. There are lots of monomers that may be residues. We know that when a polymer is manufactured from monomers, the small molecules, they link together, but you never get 100% chemistry. And so you're always going to have some small amount of unlinked, unreacted monomer present. And if it's there, then it could possibly migrate out of the plastic particle into the water, for example, or maybe into your gut if you swallowed that particle. There are numbers of common ones, styrene glycols, bisphenol A, you've heard of that. By the way, don't worry about it. This is one of those what you might call urban myths. Probably 10,000 studies of bisphenol A toxicologically, virtually no adverse outcomes, except at very high doses. So don't worry about bisphenol A. Plastics are hydrophobic. They can absorb organics, they can release organics. And they probably that chemistry exists in equilibrium because if there is, say, some unreacted styrene monomer in the particle, it could well have, it certainly is bound to the plastics because plastics are really good at absorbing small molecules. But on the other hand, if there's an equilibrium process going on, that means if there isn't any styrene in the water or in the gut, then the styrene will migrate out of the particle into the environment that it's in. And on the other hand, if there are some trace chemicals, trace organic hydrophobic chemicals in the water, for example, or in the food product, they could well migrate into the particle. So there's a lot of fundamental chemistry going on here, and it's not necessarily well defined, but it's there. Now, what about the analytics? The analytics are really tough. As I said earlier, these are very small particles. They are in a mass of other material, be it flesh or water. There are many, many other particles there too, natural particles. They could be inorganic, they could be organic. And so the challenge to the analytical chemist is to separate those small particles from the mass of material, be it flesh or water, isolate them, identify them, and quantify them. And that isn't easy at all, as demonstrated by the several years of analytical chemistry results that have been published. And the problem being that each chemist pretty much is going on his or her own experience and training, and there really aren't any standardized procedures that are being used. Many of the studies that have been done really lacked controls, so you didn't even know what to compare the number to, whoever did the analysis. Somehow, and I don't understand it, how an analytical chemist could do an analysis without having controls to know what the findings are relative to the baseline. A lot of them are like that. So you have to separate and identify those plastic particles, distinguish them from the other organic and inorganic particles that are there. And then how do they isolate them? Well, for example, if they're dissolved, which can be done with food material, dissolve and then separate, filter. Well, the filtration process then determines which particles you're going to find. If you use a relatively large filter, you will not identify the small particles. If you use a very fine filter, a micron level filter, for example, the process will be so slow because there's so much other stuff in there clogging the filter that dissuades some of the studies. So with those kinds of studies, also, it's isolating a section, a portion, usually the larger particles. And as I said before, there's very little data on nanoparticles because they're even infinitely more difficult to analyze than the microparticles. So what about foods? What do we know about some of those? Well, these are data reported in several of those studies. Think about it, between 1 and 7 microparticle per fish. Now, that's not many of anything. And it's even a question of some of them were done on whole fish and some of them were done on just fish flesh. So that creates a lot of ambiguity and interpretation difficulty. What about shrimp? Well, on average, less than 1 particle per gram of fish, so of shrimp. So if you eat a lot of shrimp, if you ate a pound of shrimp, you'd get 454 particles. We talked about filter feeders like clams and mussels, and they're the ones that are processing large volumes of water, filtering out particles like these, as well as microbes like Cryptosporidia, for example, which are about 3 or 4 micron size. So they're very good at separating small particles. And so if you eat a lot of that, chances are you'll get a somewhat higher dose of microparticles in your diet. Others, some odds and ends studies, honey and beer, and even table salt, and I'm presuming this may well be sea salt, where whatever particle was suspended in the sea precipitated out with the sodium chloride, et cetera, and was then concentrated and found. So what do we know about sources? Well, ambient seawater is one, from degradation of those floating large materials. Similar activity can occur in freshwater lakes and rivers, but also not the great amount of those kinds of waste products, but from discharges from surface runoff and from sewage treatment plant discharges upstream possibilities and wastewater. Treated drinking water can have particles, and bottled water too. So if you are addicted to bottled water, don't do it because you think you're going to get fewer microplastic particles in your diet. It actually turns out that conventional drinking water filtration processes were actually designed 75 or 100 years ago to remove particles. And so they actually do a pretty good job of taking out even these microparticles. And this is all measurable by the turbidity of the water. And at least in the US, there are very strict standards on the turbidity of surface treated drinking water. And so if that turbidity level is very low, that means there are very few particles in the water. A little bit about water analytical processes. The WHO report reviewed well over 50 studies in the open literature, and they found that 50 of them had analytical deficiencies, and so, which is very distressing, because all of those people got paid to do those analyses. And so now what we're saying is, well, but you really can't give it too much credibility, whatever they reported. As I said, also the filter size determines the size of particle that you're going to isolate and try to quantify. So large mesh filters will take out larger particles, but not smaller particles. Smaller particles won't be separated. And you have an even much more difficult problem dealing with food samples, because you're dealing with much more mass of material that is not in solution and would have to be liquefied probably to separate, which creates additional difficulties in the analytical chemistry. So here are some numbers that are taken out of the literature. These are not totally comprehensive, but you can see the ranges. For fresh water, surface water from 0 to 1,000 microparticles per liter, the larger ones. Drinking water from 1/1000th to 1,000 per liter. That's about a million-fold range. Tap surface water, maybe 300 to 600 particles, but again, questionable analytical science. Bottled water, on the order of perhaps as much as 300 or more particles per liter. Mineral water, interestingly, mineral water which is drawn directly from the ground, not treated at all, essentially, has larger numbers that they found. And the question is, how reliable are these data? And the answer is not very reliable, but they're there. Just a comment on the bottled water side. Where does that come from? Bottled water is highly processed. It goes through perhaps granular carbon, reverse osmosis. So there aren't going to be very many particles that can get through that process. Where it's coming from? It's probably coming from the packaging. It may well be coming from the cap, because the caps are routed on site at the same facility. In fact, the bottles are blown on site too. So they're routed, and in the course of grinding and routing, you probably are producing a lot of fine particles, and some of them find their way into the water in the bottle, probably. As to reliability, not much. As I say, WHO reported 50 out of the 56 that they looked at had identifiable deficiencies in the process that was used to do the analysis. And what that means is you really can't compare data across different studies, let alone within the individual study itself. So what about possible risks? Well, it's certainly undesirable to be swallowing inert particulates. It's really undesirable to be inhaling them, of course, because we know how do you get lung cancers, mesothelioma, from inhaling asbestos particles or cotton fibers or coal particles, black lung disease, white lung disease, the previous one. And so virtually anything that gets into your lungs that is not water soluble is probably going to do some damage if you get enough of them. Is that what happens in the gastric tract, in the GI tract? Maybe, but not really very much data to support it. What is known is a very high percentage of the particles that are ingested go right through and are eliminated. And so in the high 90s at least. But what about the nanoparticles? Well, they're the ones, again, that are the hardest to analyze, but they're also the ones that have the greatest potential, possibly, to be migrating through the intestinal wall or otherwise getting into circulation and then possibly concentrating in some organ, like the liver or the bladder. So there's more to do. This hasn't been observed yet in terms of humans. This has been observed in animals that have been tested animals fed very, very high doses, millions of times more than we would ever see in food. But the question is, how do you translate that into human risk? And so that's a big question mark today. Undesirable to ingest them, but not really any demonstrable adverse effect in humans yet. There are all kinds of other issues, not only the particles, but the chemicals that may be entrained in the particles, or that may be absorbed by the particles when they're in the environment. As I said, there are a number of additives that are there that could be migrating out. They may also pick up trace, parts per trillion levels of organics that are in the water, for example, could be absorbed onto the plastic particle. And then there are those that say, well, maybe biofilms that exist in water contact surfaces and in some foods may concentrate microparticles. Well, that one was pretty well dispensed with by the WHO because there's no particular reason why biofilms on plastic particles are any more of an issue than biofilms on particles of aluminum oxide or calcium carbonate or whatever. And so that one, as a unique issue associated with microparticles, is pretty well dispensed with at this point. So the chemical exposures can come from degradation of the polymer. They can come from UV oxidation and oxygen oxidation, of course. And this, we talked about leaching, and there is some potential absorption of hydrophobic chemicals, but in very minute quantities. And the WHO committee did a great number of calculations using extremely worst-case conditions in terms of quantities as well as toxicology, and pretty much concluded that none of those scenarios arrived at an amount of intake that would be significant at all relative to other kinds of exposures to those same substances. And in fact, and they were very small, with margins of safety sometimes in the 100,000 or more. So not a particularly toxicology question in terms of what the microparticles absorb. We talked about biofilms. I won't say any more on that. Treatment technology. over 90% of these are removed from by standard wastewater. And then when you get into what got into the drinking water treatment plant, if you have a conventional surface water filtration plant with coagulation and filtration, well over 90% will be removed there. So drinking water from the surface probably has very little amounts of microparticles of any type. Problem is not all countries have significant surface water treatment or even wastewater treatment in some situations. So that can be a different issue in different locations. So let's wrap it up. And pretty much from the WHO conclusions, but they're consistent with everybody else's conclusions too. Microplastics are ubiquitous. You can find them in any product, food, water, whatever. Among the foods, the filter feeders are going to be the ones that concentrate them the most. There's very little data on nanoparticles because they're even more difficult to analyze. Contaminated biofilms, if any, are not anything unusual and therefore not a significant concern. The analytical techniques, and this is maybe the most fundamental problem here, the analytical techniques are not standardized. And therefore, you have a variety of different approaches that different researchers are using, and not all of them are of the highest quality in terms of analytical science. So one key element that's necessary is standardization of rigorous, high-quality analytical science for this kind of work. On the GI uptake, it's limited, but there could be some small percent, especially from nanoparticles. And there isn't any particular concern about the toxicity of the particles. There isn't any really reliable data at this point at levels remotely close to what humans are exposed to. And they're all from high-dose rate studies, not rat studies. And they may or may not be relevant to human condition. The ultimate chemical exposures of monomers and trace organics is very small, and again, was evaluated by WHO and found to be extremely distant from levels that could cause an adverse effect in humans. There really isn't any reliable information on nanoparticles, so there's more research to be done there. And the whole issue of occurrence, exposure, and potential risk, of course, should continue to be explored. Not necessarily urgently, but it should be done so that we can decide what's important. These are the three comprehensive studies that were produced over the last few years. The most recent one is the WHO study. So I hope you are now comfortable with the next bite of food or the next drink of water you take. And thank you for the opportunity. Happy to answer any questions you might have. Thank you.